To elevate your learning experience, you have recorded classes where you can access your subjects anytime, anywhere through recorded sessions. Then you have notes based on the ultimate comprehensive book and latest CBME syllabus. And then MCQs, which are starting from beginner level to expert level. So you can buy our MCQ books and assess your knowledge. Then apart from that, we have personalized counseling sessions. So if you need any extra guidance and support other than the academic support, you can anytime feel free to book a slot with us for a counseling session. Then we have 3 different subscription plans, starting from basic, then going up to standard and mentorship, which are for 3 months, 6 months, and 12 months respectively. Then if you want one-to-one personalized guidance and live doubt clarification sessions, then you can go for the mentorship plan. And the basic plan is only for 15 months, where you have the pre-recorded class, live class, and quick revision examination modules. And then you can also get additional 20% off by using my promo code as displayed on the screen here. Then telling you briefly about our internal exam marathon series, and this is specifically oriented towards your exams that are approaching. So with this in mind, we have rapid revision of all important questions. Volatile facts will also be quickly revised. Then you have MCQ questions that will be covered so that we can assure you top-notch grades in your exams. Okay, so before wasting any time, let's begin with fatty acid oxidation. So important topics being covered first. So your fatty acid oxidation in lipids is very important. So we'll be talking about that in our first opening lecture. So the concept of fatty acid, that is, when does your fatty acid oxidation takes place in the body? So it takes place in the fasting state. That is, when the body is fasting, your fatty acid oxidation will happen. Now, if you remember, I told you that your stages of fasting, there are different stages of fasting, okay? Yeah. So beginning from, you have early fasting, then you have the fasting stage, and then you have prolonged fasting, also known as starvation. So now in your early fasting, what is happening? Your glycogen was being used. Then what happens? After your glycogen reserves have been depleted, then you enter the fasting state. And what is happening here? Gluconeogenesis is taking place. So in this fasting state, gluconeogenesis is taking place, and also the minimal amount of beta oxidation is also taking place here. But this beta oxidation is only to support your gluconeogenesis, that is to provide ATP needed for gluconeogenesis and to give acetyl-CoA. Acetyl-CoA provides acetyl-CoA and ATP. Now it is this stage, prolonged state of starvation, that is when your beta oxidation takes place. Okay, so this is the stage where your beta oxidation is taking place. So this is the entire concept behind beta oxidation. Now there are different types of fatty acid oxidation. So beta oxidation is not the only oxidation of fatty acids. There are different types of fatty acid oxidation, beta oxidation being one of them, and the most important one of them. It is for saturated fatty acid, and the most important and the most common fatty acid, saturated fatty acid undergoing beta oxidation is your palmitic acid. Then you have oxidation of very long chain fatty acid. Then oxidation of unsaturated fatty acid, oxidation of odd chain fatty acid, and minor pathways which include alpha and omega oxidation. Then moving on to beta oxidation. What is beta oxidation? Now, there is successive cleavage and release of two carbon unit as acetyl-CoA. So in beta oxidation, what is happening? Acetyl-CoA units are being successively cleaved and released. Now, why is it known as beta oxidation? Because this cleavage is taking place between the alpha and the beta carbon. Let's understand this with the help of an image. Suppose, now what are fatty acids? The fatty acids are this RCOH. So this is the where R is a long hydrocarbon chain. Long hydrocarbon chain. And it has this carboxylic acid group COH. So this is your fatty acid. Now let's understand this with the help of a diagram. Let's suppose this is your fatty acid. Okay, now it's saying that there is successive cleavage of two carbon units as acetyl-CoA. So now this is your functional group. So this is the first carbon, this is the second carbon, this is the third carbon, fourth carbon, and so on. Now we all know that which is the alpha carbon? The first carbon coming after the functional group. So your second carbon becomes the alpha carbon and your third carbon becomes the beta carbon. Now it says the cleavage is taking place between alpha and beta. So the site of cleavage becomes this. This is your site of cleavage. So this is where the cleavage is taking place. Since it is taking place, as you can see, between the alpha and the beta carbon, it is known as beta oxidation. Now, what is cleaved and released? You can see one carbon and this is the other carbon. So this unit is released, and what is this unit? This is 2 carbon acetyl CoA. Okay. So this is exactly what is saying. So this is the overall briefing or the summary of beta oxidation. So this was your fatty acid. This entire thing was your fatty acid. And what has happened, you can see there is successive cleavage of 2 carbon units as acetyl-CoA. Now moving forward to the sites of beta oxidation. Now let me, before I take this up, let me tell you the difference between acyl-CoA and acetyl-CoA. This is only for your understanding, because as we proceed, you will come across these two terms, acyl and acetyl-CoA. So your acyl-CoA is RC double bond O. Okay, and your acetyl is CH3C double bond O. So when the R is a methyl CH3, it is your 2 carbon acetyl-CoA. And here in acyl-CoA, this R is a hydrocarbon chain. Okay, and CoA, we all know it is a complex molecule which consists of, I've already told you, beta mercaptoethanolamine, beta alanine, pantanoic acid, and ADP. Okay, so that was briefly about certain compounds that you will come across while studying beta oxidation. So I thought I'll make them clear so that you don't get confused. Now, moving on to the sites of beta oxidation. So it takes place in the liver, lactating mammary gland, and adipose tissue. And the organelle is, it takes place inside the mitochondria. Now, there are 3 basic steps to beta oxidation. Very important, pay close attention. The first one is activation of beta acid. Now, what is activation of beta acid? That is your beta acids, your fatty acids, they are changed into their CoA derivatives. Okay, so when fatty acids are converted into the CoA derivatives, we say that fatty acids have been activated. So we will see how we activate fatty acids. So that becomes the first step of beta oxidation. Now this step of activation is taking place in the cytoplasm. So the second step becomes to transport these activated fatty acids to mitochondria. As we have just seen that beta oxidation is taking place in the mitochondria. So the first step is activation of fatty acid, which is followed by transport of activated fatty acid to mitochondria. And then in the mitochondria, the final reactions of beta oxidation take place. Okay. So let's take each of these steps, basic steps of fatty acid or beta oxidation in detail. So beginning with activation of fatty acids. So see, it says fatty acids are activated by being converted to the CoA derivatives. So this is the activation of fatty acid. That is, your fatty acids are being converted to the CoA derivatives. Now let's see what are the requirements and how is this taking place. So this steps require two high energy phosphates. Two high energy phosphates are required for this step. Then this is the only energy requiring step in fatty acid oxidation, and it takes place in the cytoplasm. So now two key points about this step, that is it is the only step in fatty acid oxidation. We all know that fatty acid oxidation is taking place in the fasting state and it is taking place to provide you energy. So there is no point of energy consumption. So not all these steps, only the first step, the initial step, it is requiring to a high energy phosphates. Okay, sometimes you need to invest before you can get the return. So it's the same concept. And it's the only step that is taking place in the cytoplasm as well. Then what is the enzyme involved? Acyl-CoA synthetase is the enzyme involved, and where is it located? It is located in the outer mitochondrial membrane. So after understanding this diagram, it will become more clear. So now let's understand this first step, that is the activation of fatty acid via the help of this diagram. You can see what you have here. You have fatty acid and CoA. So now you have to activate this fatty acid by attaching CoA to this. Okay, so this is brought about by this enzyme, as you can see here, acyl-CoA synthetase, which is present in the outer mitochondrial membrane. Now, what is this enzyme doing? It is converting your fatty acid into fatty acyl-CoA. You can see here, this is the structure of fatty acyl-CoA, and your fatty acids are simply this. So your RCOH has been converted to RC double bond O and OA being attached. Okay, and for this you can see one ATP has changed into AMP. So ATP is triphosphate and AMP is monophosphate. So what has been used? Two high energy phosphates have been used in this step. Now, this is also taking place in the cytosol. So this was the first step, which is the activation. Now, this activation is followed by the transport of this fatty acyl-CoA. You can see it is being transported to the transmembrane space. Between the outer and the inner mitochondrial membrane, you have the transmembrane space. Okay, now your outer mitochondrial membrane is almost permeable to all the molecules. So acyl-CoA, your fatty acyl-CoA will enter via the outer mitochondrial membrane and be present in the transmembrane space. But the inner mitochondrial membrane is not permeable. So to cross this inner mitochondrial membrane, this is brought about by carnitine transporter. Okay, now let's talk about the transport of fatty acid, that is activated fatty acid, acyl-CoA form, from the cytosol or from the transmembrane space into the mitochondria. So your activated fatty acid from the cytoplasm has to be transported to the mitochondria, as I just told you. Now a transporter is needed for this, which is known as carnitine. So what is this carnitine transporter? It is a beta hydroxy gamma trimethyl ammonium butyrate. If you don't remember this name, then also it is very much fine. So basically, you know that a carnitine transporter is needed and it is synthesized from lysine and methionine. This can form an important MCQ question that your carnitine is derived from, and your answer will be lysine and methionine. Then medium and short chain fatty acid, they do not require carnitine. Okay. Now this is also important that your medium and short chain fatty acids that is less than 12 carbon long, they do not require carnitine transporter and can pass through the inner mitochondrial membrane as such. Only long chain fatty acid cannot pass the inner mitochondrial membrane and a transporter is needed. Now for the transport, three enzymes are needed, okay? So you need a transporter carnitine. Now, what else is needed? Apart from the carnitine, three enzymes are also needed, which are carnitine acyl transferase 1, that is CAT1 in short, carnitine acyl transferase 2, that is CAT2, and translocase. So three enzymes are needed and one transporter known as carnitine. So a total of four things are needed for the transport. Now, CAT1 is located in the outer mitochondrial membrane. CAT2 is located in the inner mitochondrial membrane, and then you have translocase also located in the inner mitochondrial membrane. Once we've studied the mechanism with the help of this diagram, you will not have to mug up any of the things. You'll already be, very sequential, and you'll automatically know which is present in inner and outer chondrial membrane. So I'll just repeat this once again. Your fatty acid was activated in the cytoplasm by the enzyme acyl-CoA synthetase, for which an ATP was converted into AMP, and what was formed? Activated fatty acid was formed, that is fatty acyl-CoA. Now this fatty acyl-CoA, it enters where? It enters the transmembrane space. Now here what is happening? This fatty acyl-CoA and carnitine, they are combining together to form acyl carnitine, as you can see here, and CoA is being removed. Now this is brought about by the enzyme that is CAT1, carnitine palmitoyl transferase. It says palmitoyl because, as I told you, the most important and the most common fatty acid that undergoes beta oxidation is your palmitic acid. So you can say carnitine acyl transferase, or you can also call it as carnitine palmitoyl transferase. So what has basically happened that from that fatty acyl CoA, CoA has been removed and carnitine has been added. So you get fatty acyl carnitine. Okay, so you get this acyl carnitine, which now can be transported to the mitochondria. Okay, so for this, the enzyme translocase is involved. This translocase transports the acyl carnitine inside the mitochondria. Now, inside mitochondria, what is happening? There's another enzyme present in the inner mitochondrial membrane, which is known as CAT2 or carnitine palmitoyl transferase. Now here what is happening? From acyl carnitine, your carnitine is removed. As you can see here, from acyl carnitine, carnitine has been removed. And what is added? CoA has been added. So what you get your fatty acyl CoA back. So in this way, your fatty acyl CoA has been transported inside the mitochondrial matrix. Now this carnitine that has been removed in the mitochondrial matrix, it is transported back in the transmembrane space via this translocase again to get carnitine present in the transmembrane space for the next transport. So that was about the transport of fatty acid. I hope it's clear. It's important, so please pay attention. Now we begin with the actual steps which take place inside the mitochondria. So now we're going to talk about the actual steps of beta oxidation, the reactions taking place in the mitochondria. So you have your, I'll give you a brief summary of this. You have your fatty acyl CoA present in the mitochondria now. Now the reactions are going to take place. So basically, if we talk about these structures, although the structures are not needed, but for the sake of convenience and explanation, I'll just draw the structure. So you have your long hydrocarbon chain. Okay, I'm not drawing everything. So ultimately, what do you have? Okay. So you can see this is your CoA. This is your first carbon which has the COH group, and the second carbon just next to the one containing the functional group, that is known as the alpha carbon, and the third carbon next to it is known as the beta carbon. Okay, and then your fatty acid chain continues. Now, as I've already told you that the site for cleavage is between the alpha and the beta, so you have to cleave this bond here. Now, this bond between the alpha and beta carbon, it is a covalent bond. Okay, it is a covalent bond, and we all know that covalent bonds are strong bonds. So it is a strong bond. So it is not easy to break this covalent bond as such. We have to weaken this bond first. So what happens is you introduce a double bond between this alpha and the beta carbon. So this is your beta carbon, this is your alpha carbon, and this is your CoA attached. So you introduce a double bond. Now, to some extent, this covalent bond will be weakened. Now, what do you do? To this beta carbon, you add a hydroxyl group. So alpha, this is your beta, okay? Now, next, what you can do is, this hydroxyl is oxidized to what? A keto group. So at a beta carbon, you have keto. Now what happens? Some bond energy is shifted from this bond between alpha and beta to this carbon and oxygen. Now what you do is splitting takes place, and you split this. So this is the side of cleavage between alpha and beta, and what has been removed? A 2 carbon unit, as you can see, will be removed, and you get acetyl CoA. So this acetyl CoA has been cleaved and released, and what is left is you are left with acyl CoA, and this acyl CoA again will undergo what? It will undergo all these reactions of beta oxidation. So that was briefly about the steps or the reactions of beta oxidation. Now let's understand them with the help of this diagram given here. So you can see your second carbon here. This is the alpha carbon, and this is the beta carbon, and this is the first carbon which is attached to your acyl CoA. I hope the diagram is clear. Okay, so this was your fatty acyl CoA. Now this fatty acyl CoA, it is being acted upon by a dehydrogenase because you're introducing a double bond, okay? So hydrogen atoms are being removed. Now when hydrogen atoms are being removed, your dehydrogenases, they bring about oxidation reduction reactions. So when they remove hydrogen from a substrate, they need to give it to some other substrate. So what is this receiving substrate here? It is FAD. So your FAD receives those hydrogen and changes into FADH2. So you can see a double bond has been introduced here. And the name of the substrate that is being formed, the product, sorry, that is being formed from fatty acyl CoA is trans to enoyl CoA. So a double bond has been introduced between the alpha and the beta carbon. And the enzyme used is an acyl CoA dehydrogenase. At least you should know a dehydrogenase has been used, even if you cannot remember the entire name. And also very important that FADH2 has been formed. Now moving on to the second step. Now this trans 2-enoyl CoA, this is acted upon by an hydratase enzyme, specifically 2,3-enoyl CoA hydratase. So what will hydratase do? It will add a water molecule. You can see a water molecule being added. So a hydroxyl is being added to this beta carbon. To this beta carbon, and hydroxyl has been added. So this substrate is known as 3-hydroxyacyl CoA. Now this 3-hydroxyacyl CoA is again acted by another dehydrogenase. Specifically speaking, this is 3-hydroxyacyl CoA dehydrogenase. So again, what happens? Your hydroxyl group here has been oxidized. Your hydroxyl is oxidized to what? A keto group. Now, when something is being oxidized, something has to be reduced. So, what is being reduced? Your NAD plus, it is being reduced to NADH. So, in this step, NADH has been formed and a keto group has been introduced here at the beta carbon. So, what is formed? 3-keto-acyl-CoA has been formed. Now, this 3, now what I told you, some bond energy is shifted and you have ultimately weakened your covalent bond. So weaken the covalent bond between alpha and beta carbon. So what will happen now? Thiolase enzyme, that is beta ketoacyl thiolase, it will act and it will split. That is, cleavage will take place here between the alpha and the beta carbon, and what will be released? Acetyl CoA will be released, and what is formed? Fatty acyl CoA has been formed. Now this fatty acyl CoA will again undergo these reactions of beta oxidation. It will start from here. So which is this fatty acyl CoA which is formed is 2 carbon less, because acetyl CoA unit has been released, and this acetyl CoA, it will enter TCA to provide energy. So that was about beta oxidation. Summarizing it up quickly, you have 3 basic steps. That is activation. What is activation? Changing your fatty acid into its CoA derivative. You can see here, so what is formed? Fatty acyl CoA has been formed. This is brought about by the enzyme acyl CoA synthetase, and this is the only step which takes place in the cytoplasm, and also the only step which requires 2 high energy phosphate. Now, the second step is transport of this fatty acyl CoA inside the mitochondrial matrix. So, the transport is taking place with the help of a transporter known as carnitine, which is, I just told you, derived from lysine and methionine. And apart from these, 3 enzymes are also needed. That is your CAT1, translocase, and CAT2. Now, once inside the mitochondrial matrix, your beta oxidation reactions take place. And we've just discussed the reactions that have first a double bond is introduced, followed by a hydroxyl being introduced at the beta carbon, then which is oxidized to a keto group, and ultimately when the bond energy has shifted from between the alpha and the beta carbons, some to the carbon and the oxygen, what happens? This splitting takes place via thiolase. So you get a fatty acyl CoA which is 2 carbon less, and an acetyl CoA which enters TCA to provide energy. Now moving on to the energetics of fatty acid. Beta oxidation energetics. So if we take palmitic acid, for example, we'll understand the energetics for palmitic acid as it is the most common fatty acid undergoing beta oxidation. So it is 16 carbon long. So in one cycle, what will happen? A 2 carbon acetyl CoA has been removed. So from 16, if you remove 2 carbon, what do you get? You get 14 carbons, okay? So you get a 14 carbon acyl CoA. Then again you remove 2 carbons, you are left with 12 carbons. Then again you remove 2 carbon, you're left with 10. Then removing 2 carbon units, you're left with 8. Then removing 6 carbon, you're left with 4. Now in the last, when you remove from 4 carbon, if you remove 2 acetyl, that is, if you remove a 2 carbon unit as acetyl CoA, automatically you get another acetyl CoA. So you are getting 1, 2, 3, 4, 5, 6, 7, 8. You get 8 acetyl CoA, but the cycle is running only 7 times. Beta oxidation is taking place only 7 times, but number of acetyl-CoA produced are 8. It is very obvious because when you split a 4 carbon unit into two, you'll on itself get 2 carbon units. Okay, so this is what it's saying, that 8 acetyl-CoA are being formed. Now, acetyl-CoA entering into TCA, when they enter TCA, so each one of them, one TCA cycle gives 10 ATPs. So 8 acetyl-CoA entering will give 80 ATPs. Now, 7 times the cycle is running, beta oxidation is taking place, and per beta oxidation, what you're getting? 1 FADH2. So for 7 cycles, we'll get 7 FADH2. And 1 FADH2 in the electron transport chain, it gives 1.5 ATP. So 1.5 into 7, you get 10.5 ATPs. Now you are getting, from 7 cycles, you're getting 7 NADH. Okay, I think we lost connection. So I'll take the energetics quickly again. So we were talking about palmitic acid, that is 16 carbon long. So for every turn of beta oxidation, for every beta oxidation taking place cycle, 2 carbon units are being released. So from 16 carbon, if you remove 2 carbon, you're left with 14 carbon. Similarly, from 14, if you remove 2 carbon unit as acetyl-CoA, you left with 12. So ultimately, when you left with 4 carbon and the last fatty acid beta oxidation takes place, then splitting 4 will give you 2 acetyl. Okay, acetyl-CoA and acetyl-CoA in this case. So you're getting a total of 8 acetyl-CoA, but the cycle is running only 7 times. So we were talking about the energetics, that how 8 acetyl-CoA will give you 80 ATP, because 1 acetyl-CoA on entering TCA gives 10 ATP. So 8 acetyl-CoA will give 80 ATPs. Now in one run of beta oxidation, 1 FADH2 is produced. So in 7 cycles of beta oxidation, 7 FADH2 will be produced. So if you multiply 7 into 1.5, that is where do you get this 1.5 from? Because 1 FADH2 in the electron transport chain gives 1.5 ATP. So 7 FADH2 will give 7 into 1.5, which is 10.5. Then you have 7 NADH. 1 NADH gives you 2.5 ATPs in the electron transport chain. So 7 of them will give you 7 into 2.5, which is 17.5. So gross total of 108 ATPs. If you add all of these up, you get 108 ATPs. But as you remember, two high energy phosphates were being used in the first step. So you subtract that and you get a total of 106 ATPs. So one palmitic acid will give you 106 ATPs. So this is the net yield. Also, you must be wondering that this was okay. 16 carbon, it is an even number. So you'll ultimately get in the last step 4 carbon left and you split them up and you get to acetyl-CoA. But what if it was an odd chain fatty acid? Odd chain fatty acid. So here what will happen? You will get 3 carbon and 2 carbon units. Okay, so this 2 carbon acetyl-CoA will enter TCA, but this 3 carbon residue, which is known as propionyl CoA, this is converted into succinyl CoA, and then it enters TCA. This also enters TCA. If you remember, when we're talking about gluconeogenesis, we spoke that how propionyl CoA is only as one of the substrates for gluconeogenesis. So propionyl CoA is the only part of fatty acid which is glucogenic. So this is important. Your propionyl CoA is the only part of fatty acid which is glucogen. Moving on to the regulation of beta oxidation. Beta oxidation is regulated by the availability of free fatty acid. Okay, so if you have more free fatty acids, then your beta oxidation will take place more. Your beta oxidation is increased, and the level of free fatty acid is in turn controlled by your insulin and glucagon ratio. So glucagon increases free fatty acid and insulin decreases free fatty acid. Let's understand this with the help of this diagram. Let's suppose this is an adipocyte. And we all know the adipocytes, they have triacylglycerol tag stored in them. Now this tag, it is hydrolyzed into fatty acid plus glycerol, and this is taking place by the hormone known as hormone sensitive lipase. Now this fatty acid is what enters beta oxidation. Now this hormone sensitive lipase this hormone sensitive lipase, it is being activated by glucagon, and we all know that glucagon, when it is present in the fasting state when glucose is gone. So in fasting state, when there is no glucose, what is there? You have glucagon, and this glucagon will activate this hormone sensitive lipase, so it will cause the hydrolysis of tags and your free fatty acid increase, and there is increase beta oxidation. Okay, so that this is also how your glucagon is increasing beta oxidation in the fasting state. Now what is happening in the non-fasting state? That is when you've had your meal, there is glucose present. What do you have? You have insulin. So this insulin, it inhibits hormone sensitive lipase, and as a result of insulin, your free fatty acid level decreases. Now, this is exactly what this says, that the level of free fatty acid, it is increased by glucagon and it is decreased by insulin. Also, your malonyl-CoA, it inhibits CAT1. What was CAT1? It was the enzyme involved in transport of fatty acid. So this CAT1, it is therefore also known as gateway of beta oxidation. And this gateway of beta oxidation, CAT1, is inhibited by malonyl-CoA. And what is malonyl-CoA? This is an intermediate of fatty acid synthesis. So when fatty acid synthesis is taking place, you will obviously have this intermediate malonyl-CoA. So during fatty acid synthesis, CAT1 is inhibited. Therefore, what will happen? Your beta oxidation will not take place. So this is to avoid that futile cycle. On one hand, you're creating fatty acid synthesis. On one hand, you're decreasing them. So this is how regulation is taking place. Now moving on to the clinical. So the first one, you have Jamaican vomiting sickness. It is caused due to consumption of ackee fruit found in Jamaica. So this ackee fruit, it contains a toxin known as hypoglycin, which inhibits acyl-CoA dehydrogenase, thereby inhibiting beta oxidation. So your acyl-CoA dehydrogenase, the first enzyme in beta oxidation, that is inhibited by this toxin hypoglycin. So what will happen? Your beta oxidation will be inhibited. So there is non-ketotic fasting hypoglycemia. That is why non-ketotic, because there is decreased beta oxidation decreased beta oxidation, therefore decreased ketone body synthesis. So this is non-ketotic fasting hypoglycemia. As beta oxidation is only not taking place, so your ketone bodies which are synthesized from acetyl-CoA, they will not be synthesized. So that was about Jamaican vomiting sickness. Now moving on to medium chain acyl-CoA dehydrogenase deficiency, most common inborn error of fatty acid oxidation. There is fasting hypoglycemia, hypoketonemia, and dicarboxylic acid urea. The body is trying to find other ways to oxidize fatty acid, okay? Because your beta oxidation has been inhibited, so body is trying to somehow via other minor pathways oxidize or metabolize your fatty acid. So the other pathways are increased. So your omega oxidation is increased. Omega oxidation increases as the body is trying to find other ways to metabolize your fatty acid. Now, what happens during omega oxidation? Your dicarboxylic acids are formed. Therefore, dicarboxylic acid levels increase. Let's suppose this is your fatty acid. So this last carbon is known as omega carbon. So in omega oxidation, what is happening? This omega carbon is also changed into COH. So you get a diacid. So when there is increased omega oxidation, there will be increased dicarboxylic acid. So that is one of the clinical manifestations. That is, there is fasting hypoglycemia, there is hypoketonemia, and there is dicarboxylic acid urea. Now, MCAT deficiency is one of the causes of SCIDS. What is that? That is sudden infant death syndrome. Now, the treatment includes frequent meals, avoid starving, and meals high in carbon, low in fat. Because when you have meals low in fat, then obviously you will need to metabolize less of fatty acids. So, carnitine deficiency, it is impaired fatty acid oxidation leading to hypoglycemia. Carnitine deficiency, if your carnitine is deficient, that is your transport will not take place. Okay, so your fatty acid oxidation will be obviously affected. It will be impaired, leading to what? This will also lead to hypoglycemia. So treatment includes supplementation with diet. Okay, so that was all about fatty acid oxidation. So we come to an end of this lecture. If you have any queries, you can ask. Okay, thank you for watching. See you in the next class.